If you're familiar with AI multi-agent workflows, you might have seen some form of this architecture before. So at the top here, we provide some input to an agentic workflow, and that will ultimately kind of flow down here to produce some output in the end. Now, if we look into the boxes, typically you would have at the top here a planner agent. That's responsible for distributing work to the agents within this workflow. And then each of these agents, so let's say we've got an agent here, we'll just call this agent A, an agent B, and C. Each one of these guys does specialized work. It is specialist in a particular task. And then once it's done its work, then the results flow down here to the aggregator, and that aggregator agent prepares a response, and that's how we get our output. So that is an agentic AI workflow. But in AI, there's another architecture that we've had for quite a while that's gaining popularity, and that is called mixture of experts. And at a high level, it has a very similar looking workflow. So instead of a planner, we start with a router which receives the input and that dispatches the work. And then we have here a series of experts. So let's call this expert A, expert B, and expert C. And these guys, they work in parallel. And then at the bottom here, we have a merge component to reassemble the process tokens into a single stream. So it kind of begs the question, what's the difference between these two things, AI agents and mixture of experts? And the answer is, well, quite a lot of difference actually, but something they both have in common is they are very much part of frontier AI models today. So let's discuss what they do and how they can be used together. So AI multi-agent workflows, they perceive their environment, they make decisions, and they execute actions towards achieving a goal. And all of this happens with minimal human intervention. The agents, they typically use LLMs that have been given specific roles and tools and contexts. Now, agentic AI workflows, they're usually composed of modular components, like, for example, one module that might be the perception module. That's kind of how the agent senses or ingests information from its environment or its user input. Then there's also a component typically for memory. This is the knowledge store. That memory can be working memory for remembering the current context, or it could be long-term memory for knowledge accumulation over time, like domain facts or remembering user preferences. And then there's an assortment of specialized agents, and these are agents that excel at specific domains. So for example, we might have one specialized agent that is a data agent that knows how to query databases and clean data. We might also have a specialized agent called an analysis agent that's trained on business intelligence, and then maybe we also have a visualization agent as well that creates charts and graphs. Now, architecturally, these components, they form a loop. So there's really different stages to this. So first of all, they perceive, then they're going to consult some form of memory. Remember the memory component. From there, they're going to reason, and they're going to act based upon that reason. And then finally, they're going to observe what happens based on that action. And then kind of round and round we go in this loop. And the key here is that each of these agents operates at the application level. They're making decisions, they're using tools, and they can communicate with each other. A mixture of experts, on the other hand, that operates at the architecture level. And MOE is a neural network design that splits a model into multiple experts. So let me draw 3 experts here, although in reality there'd be a lot more. And each of these experts specializes in a part of the input space. And then there's also a gating network at the top that routes the input to the different experts in this mixture of experts architecture. And it goes through this before it gets to the next layer, coming into the merge component here, and that receives all of the responses from the experts that were invoked, and then performs mathematical operations to basically combine the output tensors from these different experts into a single representation that continues through the rest of the model. And one of the big advantages of MOE is sparsity, because only the active expert parameters contribute to that input's computation. So if we take an LLM example, let's say the IBM Granite 4.0 Tiny Preview model, well, that uses 64 different experts in its architecture, and it has around 7 billion total parameters in the model. But of those, only about 1 billion are active at inference time. So that makes it a pretty memory efficient language model capable of running on a single, pretty modest GPU. So in an MOE model, these experts, they're not separate AI agents, they're specialized neural network components within the same model. So let's consider a use case where a multi-agent workflow and a mixture of experts model show up in the same system. So let's just imagine an enterprise incident response workflow. So we've got a security analyst who's going to start this off, and they're going to start off as input by providing just an alert bundle into our model, and maybe a short natural language question like, is this lateral movement? And if it is, what should I do about it? Now, that goes into our agentic workflow, and we have a number of components there. So we have, for example, a planner agent. That's going to be the first component. That breaks up the request, and then it kind of spins up the agentic workflow and then passes it along to these specialized agents. So we might have a log triage agent here that parses the raw telemetry, and we might have a threat intel agent here that processes indicators, and so forth as we go down this workflow. And this log triage agent, that could actually be implemented as an LLM that uses mixture of experts as its architecture. So as the tokens stream in to the mixture of experts gating network, or the router if you like, that looks at each micro batch of text and on the fly decides which handful of experts inside the model should handle it. Now, only those experts, perhaps we'll go through to expert 1 and maybe expert 2, but none of the other experts, we'll just kind of leave those alone. So perhaps it would just use 2 experts out of a total of 64, and it would just activate those for that particular micro batch. So the forward pass, it's just going to touch a fraction of the overall parameters. And the selected experts, they process their slice of the representation in parallel, and then they come back down to the merge function down here that mathematically stitches their outputs back together before the next transformation layer. So perhaps this log triage agent is 7 billion parameters as an LLM, but only about 1 billion active parameters are used during inference. So agents, they route tasks across a workflow. They decide the next step, maybe call a tool, update shared memory and stuff like that. A mixture of experts routes tokens inside a single model, deciding which internal parameter slices light up the next few milliseconds of compute. And stack them well, and you get workflows that reason broadly and specialize deeply.